This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to our discussion. Today we're exploring a fascinating area of deep learning research, Kolmogorov-Arnold Networks, CAN-NENs. These networks offer a unique alternative to the ubiquitous multi-layer perceptrons, MLPs, promising improvements in accuracy and interpretability. What's the core idea behind CANs, and how do they differ from traditional MLPs?
The key difference lies in where the non-linearity is applied. MLPs use fixed activation functions at each node, neuron, while CANs use learnable activation functions on the edges, weights. Instead of linear weights, each weight in a CAN is a univariate function, typically parameterized as a spline. This seemingly small change has significant consequences.
So, learnable activation functions on edges. That sounds quite different. Can you elaborate on the practical implications of this design choice?
The use of learnable activation functions allows CANs to adapt more effectively to the specific characteristics of the data. They can learn complex, non-linear relationships more accurately than MLPs, especially in low-dimensional spaces. This is because splines are inherently good at approximating functions in low dimensions.
One of the papers mentions the Kolmogorov-Arnold representation theorem. How does this theorem relate to the architecture of CANs?
The theorem states that any continuous multivariate function can be represented as a finite composition of univariate functions and addition. CANs directly implement this representation, using learnable splines to approximate the univariate functions. However, the original theorem is limited to 2 layers. The innovation in these papers is extending this to arbitrary depth and width.
The papers also discuss the curse of dimensionality. How do CANs address this challenge?
The curse of dimensionality refers to the exponential increase in computational complexity as the number of input variables grows. CANs mitigate this by decomposing the high-dimensional function into a composition of univariate functions. This decomposition allows them to learn the function structure more efficiently, avoiding the exponential explosion in complexity. The theoretical analysis and empirical results show that CANs can achieve better scaling laws than MLPs.
The papers highlight the interpretability of CANs. How does the architecture contribute to this interpretability?
The interpretability stems from the use of univariate spline functions as weights. These functions can be easily visualized, allowing researchers to understand how the network is making its predictions. Furthermore, techniques like sparsity regularization and pruning help simplify the network, making it even easier to interpret. The papers demonstrate this through examples in mathematics and physics, where CANs helped rediscover known relationships.
One paper describes a grid extension technique. What is its purpose, and how does it improve the accuracy of CANs?
Grid extension is a method for refining the resolution of the spline functions. By increasing the number of grid points, the splines can approximate the target function more accurately. This is a unique advantage of CANs, as it allows for incremental improvement in accuracy without retraining the entire network from scratch. The papers show that this leads to staircase-like loss curves, where the loss drops significantly after each grid extension.
The papers also discuss the application of CANs to solving partial differential equations, PDEs. How do they perform in this context?
The papers demonstrate that CANs can be effectively used within the framework of physics-informed neural networks, PNNs, to solve PDEs. They show that CANs converge faster and achieve lower errors than MLPs, particularly in cases where the solution has a compositional structure. This suggests that CANs could be a valuable tool for scientific computing.
The concept of continual learning is also touched upon. How do CANs address the challenge of catastrophic forgetting?
Catastrophic forgetting is the tendency of neural networks to forget previously learned tasks when learning new ones. CANs, due to the locality of their spline basis functions, exhibit less catastrophic forgetting. Changes in one part of the network are less likely to affect other parts, preserving previously learned information. This is a promising area for future research.
The papers present several applications of CANs in scientific discovery, particularly in mathematics and physics. Can you summarize some of these findings?
In mathematics, cans were applied to knot theory, successfully rediscovering known relationships between knot invariants and even discovering new ones. In physics, cans were used to extract mobility edges from quasi-periodic tight binding models, demonstrating their ability to identify phase transitions and extract quantitative results. In both cases, the interpretability of cans played a crucial role in the discovery process.
What are some of the limitations of CANs, and what are the potential future directions for this research?
The main limitation is currently the slower training speed compared to MLPs. However, this is likely an engineering challenge that can be addressed through optimization. Future research could focus on improving efficiency, exploring different activation function parameterizations, and integrating CANs into other deep learning architectures. The potential for CANs as a foundation model for AI science is significant.
The papers mention a comparison between CANs and MLPs in terms of their scaling laws. What are the key differences?
Neural scaling laws describe how the performance of a neural network scales with its size. The papers show that CANs exhibit steeper scaling laws than MLPs, meaning that they achieve greater improvements in performance with increasing model size. This is attributed to their ability to learn the compositional structure of the function being approximated.
One paper explores the use of sparsity regularization and pruning to enhance the interpretability of CANs. How effective are these techniques?
Sparsity regularization and pruning are highly effective in simplifying CANs, making them easier to interpret. By removing less important parts of the network, these techniques reveal the core structure and relationships learned by the model. This is crucial for understanding how the network is making its predictions and for facilitating scientific discovery.
The papers discuss the potential for human-CAN collaboration in scientific discovery. How does this collaboration work in practice?
The collaboration involves a human expert using the tools provided with the CAN framework to guide the discovery process. The human can provide inductive biases, such as suggesting symbolic functions or constraining the architecture, and the CAN can then efficiently test these hypotheses. This iterative process allows for a more efficient and insightful exploration of the problem space.
The papers also introduce learnable activation networks, LANs. How do they compare to CANs?
LANs are similar to CANs in that they use learnable activation functions. However, unlike CANs, the learnable activations are placed on the nodes, not the edges. This makes LANs conceptually simpler and easier to scale, but they appear to be less interpretable and less accurate than CANs.
One of the papers applies CANs to a continual learning problem. What were the results?
The results showed that CANs are less prone to catastrophic forgetting than MLPs. This is attributed to the locality of the spline basis functions in CANs, which limits the propagation of changes during training. This is a promising area for future research, as it could lead to more robust and adaptable AI systems.
The papers mention several applications of CANs to special functions. What were the key findings?
The experiments showed that CANs can effectively represent special functions, often outperforming MLPs in terms of accuracy and efficiency. The interpretability of CANs allowed for the discovery of compact representations of these functions, revealing novel mathematical properties.
The papers discuss the application of CANs to the Feynman dataset. How did they perform compared to MLPs?
On the Feynman dataset, CANs and MLPs showed comparable performance. However, the use of pruning techniques with CANs often resulted in smaller, more interpretable networks that achieved similar or better accuracy. This highlights the potential of CANs for both accuracy and interpretability in scientific applications.
The papers explore the use of CANs in an unsupervised learning setting. What is the advantage of this approach?
Unsupervised learning avoids the need to manually select input and output variables, which can be a significant challenge in scientific discovery. By treating all variables equally, CANs can identify relationships between them without prior knowledge. This was demonstrated in the knot theory example, where CANs rediscovered known relationships and even suggested new ones.
The papers discuss the application of CANs to the Anderson localization problem in physics. What were the key findings?
CANs were successfully applied to extract mobility edges from quasi-periodic tight binding models, demonstrating their ability to identify phase transitions and extract quantitative results. The interpretability of CANs facilitated a human-CAN collaboration, where a human expert could provide inductive biases to refine the results and obtain simpler, more insightful symbolic formulas.
In summary, what are the key takeaways from this discussion on CANs?
CANs offer a promising alternative to MLPs, particularly for tasks where accuracy and interpretability are paramount. Their ability to learn complex nonlinear relationships, mitigate the curse of dimensionality, and avoid catastrophic forgetting makes them a valuable tool for both machine learning and scientific discovery. While training speed is currently a limitation, the potential benefits make them a worthwhile area of continued research.